Alright, so today we're going to talk about neutralization reactions. A neutralization reaction is a double replacement reaction between an acid and a base to produce water and a salt. Remember, a salt is any ionic compound. It can be a metal and nonmetal, or a metal and a polyatomic ion. This was a joke that we told in class. So you're going to be need to be able to predict the products and words and formulas and balance the reactions. So sulfurous acid is actually hydrogen sulfite. Remember that if you remember gingivitis, if the polyatomic ion ends in ITE, we're going to change the ending to OUS. Potassium hydroxide is just potassium hydroxide. In a neutralization reaction, we always form water, and it's double replacement, so the potassium is going to bind with the sulfite. Predicting in formulas and words, when we have calcium hydroxide and phosphoric acid, we're going to find the following. Again, we're going to have water and double replacement. To get our formula correct, we're going to need to crisscross the charges, and so that this will be our final formula. It's easiest if you change water into HOH. That allows you to not have to break up our hydroxide ion in order to get your equation to balance. When you're finished, this will be the coefficients for each of our substances. In a titration, a solution of known concentration, called a standard solution, is used to determine the concentration of an unknown solution. A known quantity of one solution is measured out, and the other solution is added from a burette until the two solutions have neutralized each other. Basically, you have equal amounts of concentration. The point at which the two solutions have neutralized each other is called the end point of the titration, and that's when you're going to be looking for a color change. An indicator is used to mark that end of the titration. You're going to be looking for color change. We're using a universal indicator, and when you use that, you're looking for a color change from pink to green, ideally, or maybe just a pale purplish blue. Phenolphthalein is an indicator that's often used in acid-base titrations. It's colorless when it's in an acid and pink in a base. This is what a basic titration setup looks like. You have your unknown concentration, that's the base, and your known concentration, that's the acid. For our setup, when we do our lab, we're going to reverse this, and we're going to have our unknown base, and we're going to have our known concentration of acid. But the best way to do a titration is to always drop the base. That's right, drop the base. Titration calculations. It's no different than what you've already been doing. We're just going to put a series of steps together. To calculate the unknown concentration of an acid or base using titrations, you're going to use the following steps. Let's see this in action. Here's our question. We've got a known amount and known concentration. Remember, this is in molarity. Is neutralized by a base of an unknown concentration with a known amount. So the first thing we're going to do is do our balanced chemical equation. I'm going to change that to HOH so it's easier to balance. Now I'm going to write down the concentrations that I know, and I'm going to write it underneath the substance in my equation just to help keep things so that your numbers don't get all mixed up. It's really helpful to do this. Now for my magnesium hydroxide, I know the amount, but I don't know the concentration. I'm going to have to solve for that. So these are shifted over a little bit. Ideally, I'd have this move directly underneath that. So step one, we're going to take our known. We've got a known molarity, we have a known volume, but we don't know exactly how many moles that is, so we're going to solve for moles. It's going to be 0.28 times 0.025 liters, and that will give you a concentration of 0.007 moles. Now that we know the number of moles of our hydrofluoric acid, we can put that into step 2. Step 2, we're taking our known moles of hydrofluoric acid, and now we're going to use our mole ratio. We're going to go up here and say there's 2 moles of hydrofluoric acid to 1 mole of magnesium hydroxide. Cross off our units, and now we'll know how many moles of magnesium hydroxide we have. The last step is to just put that in and find out what the molarity is. Remember, the formula for molarity is the number of moles per liter equals the molarity. And there's our molarity. Let's try one more. We've got a known solution here. We know the volume. We also know the concentration or the strength. It's neutralized by a known volume, but again, we don't know the concentration. So let's get our formula. Change that to HOH. Balance it. Write down what we know. We know we've got this concentration in this volume of the hydrobromic acid. We've got a known volume, but we have an unknown concentration. Step 1, take our known hydrobromic acid and find out how many moles we have. Take how many moles of hydrobromic acid we have and see what the ratio is of hydrobromic acid per moles of potassium hydroxide. Well, this is nice because it's a 1-to-1 ratio. Our units are canceling off. We're left with moles of potassium hydroxide, and now we can calculate that we've got 0.0072 moles of potassium hydroxide. The last step is to find out what concentration this solution was. So we're going to put it into the formula for molarity. Moles per liters used. And that will equal 0.31 molar, or molarity, of our potassium hydroxide solution. And that's it.
An interruption, but those students going on the TCAT trip need to report to the cafeteria at this time. Thank you.